So in today's video, we're going to graph exponential functions. This will be your first time graphing something in the form of b to the x, where b is a number, the base, and x is the exponent. So we're going to go back to a previous video where we talked about doubling your money or halving your money. So in this case, day one, we have $1 over here, and then each day that passes by, every single day that passes by, it doubles. So you have 1, 2, you double 2, you get 4, 8, and 16. And if we go back in time, which we can in this case because time is relative, so yesterday is -1, 2 days ago is -2, and 3 days ago is -3. And what happens to your dollar? Well, your dollar should be smaller the previous day. In this case, it's going to be 50 cents. Then we have 25 cents, and then half of 25 cents is 125. And if I were to continue this pattern back in time, what's going to happen to this number? This number is going to get smaller and smaller and smaller. So on day 4 days before is going to be around 6 cents, and then 5 days before it's 3 cents. So this number here is going to become smaller. But the question is, will this number ever be a negative number? Because you're getting close to 0. So what's half of 3 cents? Well, almost a penny. And then what's half of a penny? Half of a penny, which is 0.05. So this number here, if we go back in time, is going to get very, very small, but it's going to get close to 0. It will not be in the negatives because a positive number divided by a 2 will always maintain the positive. Now if you go the other way around, what happens? Well, 50, this doubles. Then what happens? It doubles. So it seems like from here to here, this number gets really, really big as the days goes on. So if we're to graph this, what does it look like? So I'm going to graph at day 0. You get 1, and then on day 1 you get 2, and then 4, and then 8, and then 16. I don't have a 32, it's probably somewhere up there. But if I go back in time, what happens? Well, a day I get 50 cents, I get smaller and smaller. So there comes to a point where I can't even draw the dots anymore, but I know these dots are going to be very, very close to the 0, but not 0, because keep in mind, you always have a fraction of $1 or fraction of a cent, depending on how small you go. So in other words, when I connect the dots here, I start off very flat, then I really curve up with the arrow. So in other words, what we have here is a special feature that I think we've seen before in one of our graphs, and that is called the horizontal asymptote. So over here in blue, I'm going to draw a little dot here, indicating that the left-hand behavior, this part here that I'm circling, it's not going to go below the x-axis or the horizontal asymptote. It's going to just taper off, level off. And you've seen horizontal asymptotes before. If you recall back, I don't know, a couple of months ago, 1 over x. This is the reciprocal graph where it sort of there's 2 arms, left and right, and over here you have a horizontal asymptote because the end behaviors, they just taper off. They don't cross this particular horizontal asymptote. The only difference between this and this is 1 over x, the reciprocal has a vertical asymptote. Exponentials do not have a vertical asymptote. They just have a horizontal asymptote. And just to recap this graph, if I were to graph this accurately based on this word problem, technically speaking, I should not be drawing and I should not be connecting the dots. The reason why is because something happens after 1 day, 2 days, and 3 days, and 4 days. If I connect them, that means something is happening within that day, by the hour, by the minute. And in this case, things only happen by the day. So technically speaking, I shouldn't be really graphing, connecting the dots. The dots should not actually be connected. So if I were to do this accurately, I should be actually taking away all these things that are connecting these dots here. So we drew a exponential function, but how is this related to b to the x? So if I were to ask you, what is the equation of this function, what would it be? So just to give you a sense of what base is the number that you're always multiplying, right? So if I say 2 to the power of 5, that means you're going to multiply 2 5 number of times. So if you notice here, there's a pattern going on. What I mean by the pattern is if you go forward in time, what's happening from one step to the other? It seems like you're always multiplying by 2. In other words, the base is going to be 2 because you're always multiplying by 2. But the question is, I think we talked about this in the previous video, how is this and this related to each other? And we talked about in the previous video, well, 2 to the power of 3 is 8. 2 to the power of 2 is 4. 2 to the power of 1 is 2. 2 to the power of 4 is 6. So there is a pattern going on from the independent variable, the input, versus the output. In this case, it's going to be 2 to the power of x. So what we're graphing here is a function which is y is equals to 2 to the x. All right, so here we're going to go backwards, meaning instead of doubling your money, everything's going to get cut in half. In other words, we have 1 over, so it's 50 cents, 25 cents, 12-ish cents, and 6 cents. And if we go backwards in time, we should have more money the day before, so it'll be 2, 4, and 8. In other words, we are doubling when we go back in time, and we are halving when we go forward in time. So if we're to graph the shape of this graph, okay, the shape of this graph would start off at, well, I shouldn't say start off, the y-intercept is 1, but if I go back in time, so -3 and 8 is all the way up here, and then -2. So in other words, we have a graph, get smaller, 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 smaller. I shouldn't be connecting the dots, so I'm just going to put a little dash. So I'm not connecting the dots, I'm just trying to show you the flow of the shape. So we have a graph that is actually decreasing in this case. So if you compare the previous graph and this graph, it seems like these two graphs have a different type of behavior. This one goes down, whereas the other one increases. And here we also have a horizontal asymptote. I'll use red to indicate that there is a horizontal asymptote, because if you keep on going in time, this number here gets small, small, and very, very, very small, but these numbers will never drop down below the negative number, because this is a positive, you divide it by 2, it still maintains as a positive number, it just gets very, very small, close to 0. And we call this horizontal asymptote at y is equals to 0. So how is this related to y is equal to b to the x in terms of the equation of this? Well, what's happening from one step to the other? So as you go from top to bottom, what's happening? You're always multiplying by half or dividing by 2. So I want to think in terms of multiplying. So in this case, my base is going to be 1 over 2, because you're always multiplying by 1 over 2. And there is a connection. In this case, it's going to be 1/2 to the x. We actually explained this in the previous video, so I don't want to spend time explaining why these numbers represent 1 over half x, but it is. In other words, you're actually graphing 1 over 2 to the x indirectly, because we're not connecting the dots. So from the two previous examples, one was increasing, growth we call it, and the other one was decreasing, it was going down, we call this decay. So what is it that makes a function go up, increase? So we're going to talk about this new word that I mentioned about ratios. Ratios is a number that you multiply to get from one to the next. So I want to make this 1 bigger. What type of number should I multiply by 1? Well, before we doubled it, we can triple it, we can quadruple it. So in other words, we can multiply a number that's bigger than 1. But miss, what happens if I take 1 times 1.1? Well, let's have a look. So 1 times 1.1 is 1.1. But if you take 1.1 times 1.1, do you think you're going to get a number that's bigger than 1.1 or smaller than 1.1? So you put this in your calculator and you end up getting 1.21. So as you can see, this number is getting slightly bigger. You take that number again and multiply by 1.1 and you get 1.331. So what I'm trying to say here is that if you multiply a number, when the multiply a number that's bigger than 1, the number you're going to get is going to be bigger than it was before. Meaning if you're to graph these points here, it's going to be increasing. So in other words, if the base is greater than 1, meaning you're multiplying by number that's more than 1, it's going to grow. It's going to increase the graph. Not the other way around. So what number do you multiply to give you a number that's smaller than 1? You wouldn't double it or triple it. You would multiply a number that's a little bit smaller than 1, such as, let's call it, well, before we actually multiply by half, let's just multiply by, for example, 0.1. Well, what happens if you take 1 times 0.1? You get 0.1. What happens if you multiply again by the same ratio? You get 0.01. And over here, so as you can see the pattern here, as you can see, we get more decimal places, more decimal places. So in other words, these numbers are getting smaller. So when the base, meaning the number that you're multiplying, is less than 1, what's going to happen, and above 0, because we want the base to be not go into the negatives, what's happening is that this number is going to decrease. And for those who are wondering, well, miss, why can't my base, the number that I multiply, be a negative? And so for this concept here, I'm going to actually explain in a live lesson why the base cannot be negative. So as of right now, based on these examples here in this format, this base here must be positive and it must be greater than 0, which is the same thing as being positive. And there's one number that the base cannot be. So what does that mean? So what is a number, if I were to give you a table here, let me just erase this. There is a number that you multiply will not actually get bigger or smaller. What is that number going to be? Well, there's only one number that neither gets bigger or smaller, is going to be 1, because if you multiply by 1, it's still the same. So in this case, b cannot be 1, because an exponential graph only has two ways of behavior, either increases or decreases. It cannot be flat, meaning if I were to graph this, we actually get a horizontal line. So that we do not consider, that's a linear, that's not exponential. So when it comes to the base, for now, I'll explain this later, but the base must be positive and the base cannot be 1. So as I said, I'll explain why this cannot be negative in a live session. So here we have a Desmos where I typed in b to the x, so a general statement. And what's next is I'm going to take the function and change the b value. So over here, as you can see, I'm just moving it around. So if you notice here, I'm going to let b be 1. Try to be, so if you notice here, it's flat. Well, hold on, it's flat. Because we just said that when you multiply the base by 1 many, many times, 1 times 1 times 1 will always be the same. So it's a flat horizontal line. It's not exponential behavior. But if you make it bigger than 1, so I'm going to slide this over to the right, what happens? The graph is, the base is 1.25, because when you multiply 1.25 many, many times, that 1.25 is going to get to be bigger. Now, if I make it larger, so as you can see here, the base is positive and it's greater than 1. So you can see that the graph is getting more curvier, more steeper as the base gets bigger. So this here, the red graph is increasing. But let's go back. Let's actually go back to the flat one. And let's go a little bit below. What happens? Oh, when the base is less than 1, all right, it's decreasing. It goes from high then to low. It flattens off-ish. All right, so what happens? This is what happens. But what happens if the base is 0? You have nothing. So you can see there's nothing going on. It's like a horizontal line-ish, which is not exponential. Now I'm going to move it to the negative side. If you notice here, they're negative. If the base is negative, you don't have a function. And Desmos can't even graph a function, and there's a reason why. As I said, I'll explain this in a live session, why you can't have a negative. So let's go back to the graph here. What kind of features are in common here? I want you to stare at the y-intercepts. So as you can see, as I go from left to right, look at the y-intercept. It seems like the y-intercept doesn't change. It's always at where? Over here, over here. It's always at 0 and 1. So that's one thing they have in common. And if you notice all these graphs here, they seem to be always in the positive. The range is always positive. It never falls in the negative. And also there's one thing they have in common. They have a horizontal asymptote, which is the horizontal barrier, which prevents the graph from dipping below the x-axis. So there's a lot of things they have in common, even though the shapes are slightly a little bit different. So as I go back here, right? So the y-intercepts are the same. It's always, the range is always y is above the x-axis, even though the behavior changed. You got decreasing and now you have increasing, but the y-intercept is the same. So these are the features they have in common. So here we have a part of a graph, just 4 dots. And if we were to look at this graph, if I were to ask you, well, is this function, are these 4 dots forming a parabola type feature or a exponential feature? Because if you don't notice both the behavior, it seems to increase. So this is where we have to be careful and we have to analyze the numbers. So I'm going to take these numbers and create a table of values. Over here, I'll put the x and the y, and all I'm going to do is just copy the points, 4 points to the left and right. So 1, 2, and then you have 2 and 5, and then you have 3 and 10. So the question right now is, are these numbers forming an exponential pattern, or are they doing forming a quadratic pattern? Now keep in mind, we need to go back to grade 10. If you want to show that this is quadratic, remember in grade 9 first, you actually calculate the first differences. If the first differences were all the same, it would be a linear, straight line. Now let's have a look at the first differences. Well, from here to here is +1. 5 minus 2 is 3, and 10 minus 5 is 5. So we can tell right away this is not a linear because you're not going up by the same amount. And clearly the graph clearly says it's not a straight line. It's a curve. Now the second differences are the following. Now if the second differences are the same, in this case 3 minus 1 is 2, 5 minus 3 is 2. So in this case, because the second differences are the same, we can say that this is a quadratic and it's not exponential. Now, if you want to show it's not exponential, here is what I'm going to show you. So exponential means we don't have first differences or second differences, we have ratios, meaning what number multiplies to get to the next number. So you have to ask yourself, well, 1 times what will give me 2? All right, times 2. 2 times what will give you 5? Well, 2.5. Well, how'd you get that? Well, we took 5 divided by 2 to get 2.5. What about from 5 to 10? Oh, you're going to double it, meaning times 2. So notice the ratios are not the same. You're not always multiplying by 2, 2, 2. They're not the same. Because the ratios are not the same, we cannot say it is exponential. It is not exponential.